All right, let's do some calculations with acid and base reactions here. What volume of 0.1 molar hydrochloric acid solution is needed to neutralize 25 milliliters of a 0.350 molar sodium hydroxide solution? Now, technically, whenever I'm doing some kind of a stoichiometry or anything like that, I want a balanced equation. So I'm going to assess the situation here. I've got hydrochloric acid and sodium hydroxide. Classic neutralization. The HCl, the sodium hydroxide. If I start this like a first year equation, it's a double replacement. I get sodium chloride, hydrogen hydroxide, or water. Everything's +1, -1, so technically I'm done. Now, if I'm doing stoichiometry, it's not necessary that I scale this down to net ionic. I really just want to know the ratio between reactants and products. I want to know the formulas, all that good stuff. If I were asked to scale this down to net ionic, watch what happens. HCl is a strong acid, so it splits into hydrogen and chlorine ions, extensively ionizes. Same thing with sodium hydroxide, strong base. So this is really sodium and hydroxide ions. On the product side, anything with sodium is aqueous. Most chloride solutions are aqueous, except for silver, mercury, and lead. So there's no doubt this is aqueous. But we do not get to split the water. Technically, water would be a liquid, and everything else would be aqueous. And when I'm doing the whole net ionic thing, I'm really only looking at things aqueous in solution. Okay, so now we would look at both sides and try to find any common ions, any spectators that don't change as a result of this reaction. Sodium, you are the exact same thing on both sides, +1 ions. Chlorine, you are out. Chlorine ions on both sides. Watch this. Here's your net ionic. It really just scales down to hydrogen ions and hydroxide ions producing water. Sometimes people look at this and think something's wrong. That seems way too simple. Nope, that's right. The sodium and the chlorine are spectators. They're aqueous on both sides. They do not change as a result of this reaction. It's just the hydrogen and hydroxide forming water. Now again, this was not necessary to solve the problem, but I just wanted to show an example of a strong acid, strong base, because I think in the last video we had like a weak acid, strong base, and a strong acid, weak base. Here's a strong. All right, now let's do the math. So I have some sodium hydroxide. I have 0.35 molar sodium hydroxide. 0.350 molar, I should say, because that 0 is going to allow me 3 sig figs. Molarity equals moles per liter. I got to switch it to liters. So this will be like 0.0250 liters. Up on top, that's 25.0 milliliters. That is 3 sig figs. So if we cross multiply, this gives me 0.00, let's go 875 moles of sodium hydroxide. Now if I look at the balanced equation, and I'm showing the balanced equation, everything's 1-to-1 ratios. So if I need to neutralize this sodium hydroxide, I need the same amount of moles hydrochloric acid. I know the molarity of the acid, 0.1 molar hydrochloric acid. I want to know what volume. I'm going to need 0.00875 moles of it. We're going to solve this for liters or volume. This is true. This is HCl. I'll write that down one more time. Because it's a 1-to-1 ratio in the balanced equation. And I showed the balanced equation, so that's kind kind of proving that I knew that the moles of acid and moles of base needed to be the same. Excellent. So we solved this for volume, and we're all set. This is volume coming out in liters, so I'd be looking at 0.0875 liters. Or if that bothers you, you can switch that back to milliliters, 87.5 milliliters. That looks like a weird 7. That's going to bother me. 87.5. And if it doesn't specify on the AP test, either would be acceptable. This one doesn't specify. Now, sometimes they will. They might say, like, what volume? In milliliters. So watch for that when you're reading through the original problem. Otherwise, this one is done. A lot of acid-base stoichiometry really is just that. It's a lot of looking at the ratio in the balanced equation. It's often 1-to-1s. This next one, I really enjoyed. This was fun. Let's get the equation down. In an experiment, 28 milliliters of a 0.25 molar nitric acid solution, 53 milliliters of a 0.320 molar potassium hydroxide solution are combined. Calculate the amount of water formed. And then we want to know the concentration of any excess hydrogen or hydroxide after the reaction has gone to completion. That's the part I like. There's a little limiting reactant twist to this one. Let's survey the scene and check out the balanced equation because I'm going to need to know the ratio. I've got nitric acid, hydrogen nitrate, and potassium hydroxide. Let's do a little switcheroo. We're going to get potassium nitrate. And there it is, water, HOH. Now again, if I wanted to, I could scale this to net ionic. I don't have to. I really just want the ratio in the balanced equation, which I have. This is all +1 -1. Hydrogen nitrate, potassium hydroxide, that sucker's balanced. All the formulas are balanced as well. Okay, so that's going to be nice, 1-to-1s. So let's see what we have here. We know we're going to make water, but the amount of water formed is going to be dependent on which of those reactants runs out first. So let's get these into moles. Let's do moles of each reactant. We've got 0.250 molar nitric acid. Molarity is moles per liter. 0.0280 liters. Let's leave this as 3 sig figs. 0.00700. That's nitric. HNO3. Now we'll do the other one. We've got 0.320 molar potassium hydroxide. Molarity equals moles per liter. What do I got? 53 milliliters. 0.0530 liters. Cross multiply and I have 0.0170 moles of potassium hydroxide. Okay, so I like this. Now I got moles. I want to figure out limiting and excess. It's a 1-to-1 ratio, so automatically whichever one has less moles is my limiting reactant. So in this case, it's the acid, it's the nitric acid. So the potassium hydroxide is in excess. Okay, so if I look back at the problem, at the end it says, what is the concentration of hydrogen and hydroxide in excess after the reaction goes to completion? Well, guess what? There's not going to be any excess hydrogen. I can cross that off right away. The hydrogen from the acid, that's the limiting reactant. That will all be turned into water. So I really only have to focus on the hydroxide when I get to that point. There will only be excess hydroxide. All right, so the amount of water formed is dependent on the limiting reactant. Now, they don't specify a unit for the amount of water formed, but I think I can get around that. if we go 0.00700 moles of the limiting reactant, HNO3. When I do the stoichiometry, I'm always going limiting reactant to whatever I'm looking for. In this case, it's the water. Now I kind of like to get my units all in a row, and I like when they cancel. So I'm going to cancel the nitric and switch it over to the water. I'll say water, H2O. I get it, it's a 1-to-1 ratio, but again, like something makes me feel really good about going like this. My units cancel, I know I'm on the right track. Now I'm going to switch it over to water. I'm going to cancel moles. And I'm going to put it in grams of water. And I'm going to look up the molar mass on the periodic table. And I'm going to say like 18.02 grams. Because if I plug this in my calculator, I'm going to be looking at about like 0.126, yeah, grams of water. Unless otherwise given, you can always assume that the density of water is 1 gram per milliliter. So like technically, if I was really doing this in the lab, I'd probably measure an amount of water, I don't know, grams, probably milliliters. So I might want to say then that this would be like 0.126 milliliters, because a milliliter and a gram should be equivalent when we're talking water. 26 milliliters. And technically, they don't specify a unit, so even if you left it as moles, I guess I couldn't fault you for that. But I'm going to leave it as either grams or milliliters in this case. All right, part 1, check. We've got the amount of water formed. Now let's move on to this excess. So we already figured out that the excess is going to be hydroxide. There will be no excess hydrogen. Okay, so we have to figure out how much hydroxide gets used, and then we'll figure out how much hydroxide is excess. So here's what we had. We had 0.017 moles of this KOH. That's what we have. Now again, since it's all 1-to-1 ratios, we're only going to use 0.007. And if it wasn't a 1-to-1 ratio, I'd want to calculate that. I'd want to look at the balanced equation. I'd want to look at the ratio and figure out, okay, here's the amount of limiting reactant that I have, how much of the excess will get used. But in this case, with a 1-to-1, I know I'm going to react 0.007 moles, which leaves me with the excess, 0.0100 KOH in excess. All right, so now here's the part where I usually see the most common errors. We got the amount in excess. It wants to know the concentration. Concentration means like molarity. Okay, so we got the moles. We just got to go moles per volume, right? Moles per liter. When you do this volume piece, sometimes AP problems will say like assume volumes are additive. Or if they don't specify, you can always assume that volumes are additive. So I'm going to have 0.0100 moles of KOH, and technically the potassium's a spectator ion. I'm really just concerned about the hydroxide. We want to divide this by the total volume after you combine the two solutions. And so this would technically be in milliliters, but I'm going to use liters because molarity is moles per liter. So this would be a combination of the 0.028. That would be liters of the original acid. And then the 0.0530 liters of the base. So sometimes they'll say that. They'll say volumes are additive. If they don't, you can always assume that when you combine those two solutions, you can just add the volumes. Now, technically, we're maybe forming some water, and so maybe the final volume would be a hair less, but it would be so small that you wouldn't even be able to measure the difference in the lab. So we can always assume that the volume is additive. And then we plug this in our calculator, and we say 0.123 molar hydroxide. There's the concentration, the molarity of the excess hydroxide ion.